So this is chapter 7, concepts, question 3. The Laplace transform of a function f of t, which is blah, blah, blah. Okay, it's defined by the integral 0 to infinity e to the negative st times f of t dt. Find L of 1 and L of t. Did you want to do both of them or
Yeah, we can do both just because I don't really know how to start this problem.
um yeah, sure. Let me write down the questions. So general Laplace transform. The notation is a little funny. I'll explain that here in a moment. You actually see this in differential equations. If you guys take Math 275, you will actually see Laplace transforms. They're kind of cool. So we're going to look at L of 1 and L of t. So I'm going to go to my other video here. In the first case, you're actually taking a transform of a function. And in this case, the first case, the function is 1. So this whole thing is just 1. So L of 1 is just the integral 0 to infinity e to the negative st times 1 dt. Now, this is an example of a improper integral because it has infinity for a bound, but it can still be worked out. What we need to do is just kind of treat it as a limit. So I'll use b as the upper bound. And then we just integrate. It's negative 1 over s e to the negative st being 0. We take the limit. I'll write it out. In the second case, that's just 1. So this whole thing is just 1 plus 1 over s. In the first case, we do the lim as b goes to infinity. Well, you're raising e to a very large negative number. And that means, in a sense, e is sitting in the denominator and it's going to overwhelm everything. So it's going to trend, this whole thing's going to trend to 0. So you end with 0 plus 1 over s, which is just 1 over s. Okay. That's an example of just a convergent improper integral. And so this one worked out. This was like one of the first sections of this module, like 7.1 or 7.2. For L of t, it's e to the negative st times t dt. And we need to actually use integration by parts here. And so I split it up as u as t and dv as e to the negative st dt. And let's just kind of put it all together. So it's u times v, so it's negative t over s e to the negative st minus integral v to u. So this is actually going to, with minus here, the minus here, going to make a plus. The 1 over s can come out in front. Okay. I'll pause here. Does that make sense what I did?
Mhm.
Okay. Um, well, oh, you know what? We got a little lucky here. We actually just figured this guy out. We got that from a couple seconds ago. So we'll just go ahead and pop that in. Right here, we still have to do the limit. So as the bound goes to infinity, you actually have a situation where you have, if I move this into the denominator, The t is on top, the s is on the bottom, and then the e to the st is on the bottom. And what happens here is that the exponential function outgrows the linear numerator. So this whole thing goes to zero. You could also show this using L'Hopital's rule. And you end up with just 0 plus 1 over s times 1 over s, which is 1 over s squared. And that's the Laplace transform of t. So what you're seeing here is just kind of an application of improper integrals. Um, this is something you will see when you get to differential equations. Now, the good news is that when you get to differential equations, you don't necessarily have to work them all out all the time. Oftentimes, you're just given a table of of Laplace transforms, and you just have to memorize them. Does that make sense?
Oh yeah. Yeah, that's
Okay,
really.
any questions on that? This was number 3 on the chapter 7 concepts on affinity. So in case you're wondering, and if you want to take a moment to uh, maybe take a screen capture of that, you can go ahead and do that. So this is in the chat. It's 8-1 question 6 review document. It's okay. Let me write it down here. So it's a sub n 5 to the n plus 2 over 6 to the n plus 2. This is 8-1 question 6. And you know what? Let me find it. I think I know where that is. That's on the. Give me a second here. I have to go to my ASU site. I'm going to go to the Canvas. Everything's it's like I'm finding Easter eggs here. Just got to look for them. Okay, I found it. All right, so I'm going to share the screen. I just want to make sure I wasn't missing anything here. So this is what you're looking at here. We're looking at the behavior of sequences. Basically, does it converge or diverge? And we're looking at this one right here, number 6. Sorry about that. So we just want to say, well, what happens as n gets large? Alrighty. So, well, a couple ways to do this. We can be clever with the algebra. Um, Notice I can write 5n plus 5 to the n plus 2 is 5n times 5 squared. And the same for the bottom. And those just become constants outside. And I'm actually going to write it this way. I think it's a little cleaner. But if you take a fraction less than 1 and raise it to a higher and higher exponent, this will tend to 0 as n tends to infinity. So the long-term behavior of this sequence is it tends to 0. I should note that it never actually equals 0, but it gets close to 0 as a limit. And on a sequence, especially, you can actually bring up like an Excel sheet. Or actually, just do it in your calculator. Enter it as a function and just type in a big number for n and see what happens. And you'll see that it starts to trend to 0 asymptotically. That was John's question. John, did that help?
Yeah, no, I understood it. I just wanted to make sure I understood that, like, if like for showing the work and stuff. I thought it was pretty simple and straightforward, but I was like thought it might not be that easy.
Um, Well, sometimes they can be. Generally speaking, when you get something that's kind of creative like this, I tried to trim it down a little bit. I tried to get to the good stuff, which was this 5/6 to the n. Because the 25/36 out front ultimately is not going to do much. It's all the actions happening with the 5/6 to the n. And that's really what's going to govern whether this thing's going to converge to zero or not. And in the big picture, when you get to the rest of chapter 8, we're actually going to be looking at series that converge. And one of the necessary conditions for a series to converge is that the sequence converges to zero. If the sequence does not converge to zero, the series diverges. That's like a little stepping stone. So I'm sharing the screen. This is number 3 on 7.6 review document. If this was the one you wanted me to look at, let me know. If not, let me know. Let me copy down the information. Consider a tank in the shape of an inverted circular cone of height of 20 meters. So I'm copying my information down as I read it. A top radius of 4 meters. Using 9.8 meters per second squared as the acceleration due to gravity. What do we got going here? 1,000 kilogram per cubic meter for density. Set up an integral for the work required to pump the water out of the tank if the tank is full of water and being pumped out of a 1 meter long vertical spout. So I'll tell you what. So let me just copy down full of water, 1 meter spout. Second one would be half full. I guess it'd be one at a 0.5 millimeter spout. The third one is just being pumped over the top. The last one is you just want to pump half the water out of the tank over the top. Okay. If I can get one of them set up, the rest kind of follow. They're just cosmetic changes. This is a good question. These questions, they really kind of test your ability here. So we have full water. So here's the idea. That's an inverted cone. I'm looking at it straight on, but it's actually a conical shape. If I take a random, let's say I take a representative shape here, that's like a slice. And in reality, this slice is actually a circular slice. And the volume, and we have a radius here. So the volume is going to be pi r squared h for the volume of the slice. And um, well, the h is just going to be your dx. So I'll just go ahead and jump to that because it's the thickness. We need to come up with a formula for this little radius here. I'm going to use x for radius. So what I'm going to do here is just create a formula so that basically it's a line between 0, 0 and 420. So the line here, pardon my arrows, that would be y equals, the slope would be 20/4, it'd be 5x. Okay. So that means x would be y/5, or my radius over 5. Now I'm getting some letters here. I should actually not be using dx. I should be using dy because I'm slicing vertically. Sorry about that. Now, one thing I want to check when I set these guys up is that when I plug in, let's say at the top of the tank, y would be 20, 20/5 is 4. Okay, that agrees. And at the bottom of the tank, y would be 0. And of course, that 0/5 would be 0. So this seems to work. So it looks like I've got a formula going. I've got pi over 25 y squared dy. And then now I can get going on my work integral, the 9.8, the 1,000, and the pi over 25. I'm kind of thinking to myself here, yeah, I want to put that out there right now. Yeah, sure, why not? I'll put all the constants out in front. And now the thing is I'm basically pumping everything out of an extra meter. So I need to come up with a formula for the height to account for that extra meter. The idea is that when if my bounds are going to be 0 to 20, at the top, I should only be pumping it out 1 meter. And then at the bottom, the stuff that's at the 0 should be being pumped out 21 meters. So it looks like I should have 21 minus y as my um, distance. And then, of course, I've got this y squared to deal with. And then dy, and that looks good to me. Let me just kind of stare at that myself, make sure I'm happy with it.
I think
Yeah,
that's actually the standard answer for this problem.
yeah. You know what? I'm actually going to look at it myself. Yeah, I'm curious. Yeah. Well, how about that? I did it right. All right, cool. Hey, maybe I'll take the test. Um,
Sorry, where does the y come from? The y squared come from?
so you're looking at the conical tank from the side, and since I've oriented it vertically, I'm just going to go ahead and use the letter y as my variable. I take a slice here, but then I realize that the slice is actually a circular slice, like a hockey puck. And I need to come up with a formula for its volume. The volume is going to be the circle times the thickness. The circle is pi r squared. The thickness, I called it h for a moment. The h just becomes your dy because it's like a little tiny change in y. And so I had to actually figure out an equation for y in terms of x. So y was 5x, therefore x was y over 5. That's where the y over 5 came from for the radius. You can see the radius would be right here. And the 5 squared just moved out here, and then the y squared stayed here. So I moved out all the constants to the front. Does that answer your question?
Sort of. Let's just move on.
So the question is, where does the 5 denominator come from again? You're trying to come up, see, if you look at this face on, this little distance here, which I've labeled x temporarily, is the radius of this circular disc from the y-axis to the edge here. So I need a formula that relates the sides here. So the point 0, 0 to 420 is actually given by the line y equals 5x. Therefore, x is y over 5, and that's where the 5 in the denominator came from. So I'll draw the little arrow to kind of show the logic there. As far as the follow-up questions, half full, half a meter spout, I would change that 21 to a 20.5. Well, actually, no, I take that back. Let's think about this. The water would be sitting from 0 to 10. So the water at the 10 meter level would have to be pumped out 10.5. Yeah, actually, so 20.5. Yeah, that makes sense. So that's the way I do it. I just kind of think it out because you have to build in this distance. Work is force times distance, and you have to build in this distance term. So for the case of part B, this is part A. Part B would be all the same stuff. Nothing really changes except bounds would be 0 to 10. We're only pumping it out a half a meter spout above the top. And same everything else, dy. That's really it. That's really the only changes. And then for part C, it start off full. Actually, right here, you just make that a 20. Everything else would stay the same. And then for part D, that should be a D. We're only going to pump out half. And so I guess we're just going out over the top. I would keep this as a 20 and I would go from 10 to 20. Because I'm pumping out the bigger half, if you will. There was a question on ed discussions regarding the use of the word half full, and whether it was half the height or half the volume. And the answers would indicate they meant half the height. And I agree, the wording is a little vague. The problem would be that in a lot of these, to find the half the volume, to find the height that corresponds to half the volume, would be itself an integral. So I'm pretty sure that was not the intention to throw another integral at you. Alrighty, does this help? Again, this was David's question originally, and I'll center it. I apologize if it looks a little blurry. Does that help explain the setup?
Yeah, it definitely helps to think of them of the displacement as a separate distance as a separate variable from the depth of the liquid.
Yeah, yeah. These you just kind of. I've always found that there's a certain amount of formulaic development, but sometimes, like for example, right here, figuring out this 21 minus y, I just thought it out. I said, well, the water at the top, represented by the 20, has to be pumped out 1 meter. So 21 minus 20, well, that will make 1. And the water at the bottom will have to be pumped out 21 meters. Well, 21 minus 0 makes 21. So that's how I work it out. I just said, well, that would have to be the equation for at least the distance part. And then the rest of it, I mean, this is actually a pretty easy integral. These are not that hard. And then this is just calculator work. Any other questions on this one? Well, that was a good one. I should mention, like on test 1, you're going to find that a lot of the questions, you have a few where you have to work them out. There's also a lot where you just simply choose the right integral. So you might get this, let's say you get this question on the test. And it says, what integral represents, scenario A? And you might have like a half dozen choices. And that's kind of the thing you might be looking at. So you might only just be getting to the setup stage. And that's as far as you go. So just be aware of that. 2 when I was a student. All right, so I'm going to share the screen. Number 4, a heavy rope, 50 feet long. Let's get that going. 50 feet long. Weighs half a pound per foot. Hangs over the edge of a building 120 feet high. And by the way, the height of the building is irrelevant. It just needs to be taller than 50 feet because otherwise it sits on the ground. So, all right. How much work is done in feet pounds to pull the rope to the top of the building? And then how much work is done in foot pounds to pulling half the rope to the top of the building? Okay. So let me write that down. So A is we're pulling the whole rope up. And B, we're pulling just half of it. Okay. Hold on a second here. Okay. Ironically enough, the actual integral for these things aren't that bad. You have an integral, so you're pulling the whole thing 50 feet, so 0 to 50, 0.5 x dx. And I'll let me go through the explanation there. One way to think about it would be let's say you just pull it up 1 foot. Well, you're pulling up 50 feet, so that's 25-pound rope because 50 feet at half a pound per foot. So if you pull it up 1 foot, that's 25 pounds times one. So, you can actually just work that out. You need your integrals, just 25 times one. So foot pounds, 25 feet pounds. And then you do the next one. So now uh, you're pulling up 49 and a half feet of rope 1 foot. And so that's what, 24.5 pounds. So you basically you could actually chop it up into like 50 little questions and just add them up. But that's the essence of an integral, in a sense that an integral is just really a gigantic addition question. And so ironically enough, it's just simply the weight per foot times the feet, really. And that's all it is. So this one just works out to be, what does that give us? 0.5 over 2, so 0.25 x squared over 2 from 50 to 0, whatever that is, calculator. I get 312.5 foot-pounds. Okay. Does that make sense? I mean, these are kind of deceptively simple, aren't they?
So what on some of these acceleration due to gravity comes into effect, and since I haven't taken physics,
That's a
can
good
you
point. Pounds in the imperial system is already a force. You do not need to incorporate gravity if it's already in pounds. If you're given something in terms of kilograms, you do need to convert it to newtons by incorporating gravity. We usually try to make that really clear in the question. Okay, that's a good question. It's a common I guess you could say, point of confusion. Ironically enough, in the imperial system, using pounds, you actually are at an advantage because it's good to go. It's already like ready for the integral, and pop it in, you're done. Does that help?
So on some of the questions, they kind of assumed that we knew some of these constants. Are we going to be given uh, like the 9.8, I think it was, or
Yeah,
something?
you should be given, like if it's metric, you'll be given the 9.8 for the gravity. You'll be given obviously any density information because obviously that's stuff you don't memorize. And you can treat this 0.5 up here like as a density kind of. For the next one, ironically enough, it's just you're only pulling up half of it, same basic integral. You get 0.25 over 2 x squared from 25 to 0. Now, this isn't the complete problem. Let me get the number for this. 25 squared times 0.25 divided by 2. Oh, my bad, my bad. This should be 25 to 50. Because you're okay, my bad. Ah. So this is 0.125. This would be 50 squared, take away 25 squared. Let me do that again.
Can I ask a question?
Yeah.
Wouldn't it be the integral be 0.5 over 2 or 2.5? Are you dividing it twice or am I mistaken?
No, I'm still pulling up this 0.5 is the density figure for the rope.
Right. But then you go to 0.25 divided by 2 because the x would be x squared divided by 2.
Oh yeah, of course, yes. Oh, you know what? You're right. You're right. Oh boy. Yes. I messed that up. Yeah, excellent point. I actually did it twice, didn't I? Gosh darn. All right, you know what? My bad. This is getting messy. Huh. Sorry about that. So 0.25 x squared. Let me just do it real quick. You know what? I actually had the original bounds were correct because I'm starting at the top. So I'm treating the origin as the top. So that should be 0. And I'm pulling up the first half of the rope. So I should have it 25. So I think I got myself turned around there. So 0.25 times 25 squared. Yeah, it works out. Okay, 156.25 foot-pounds. Now, this is not the end of the question. You still have the other half just dangling. You can treat the other half as just basically as um, a dead weight, because it's not being pulled over, it's just being pulled up. So you're literally just lifting. It's basically, how do I write this? The balance can be 25 to 50, or actually, this is as long as it sums to 25. But we're pulling up 25 pounds of rope here. So what do I get when I do that? That's point. Yeah, there we go. Because this just works out to be 12.5. When you integrate it is 12.5x. And I just popped in the bounds. The thing about this is you could have used any bounds because this is just a constant. You're just integrating a constant. What does that work out to be? Times 312.5. Yep. And then you add these. So 468.75 footballs. Actually. All right. Sorry for the confusion there. I got a little sloppy.
Just to clarify on this one,
Yeah.
the first integral 0 to 25, um, does that not represent the second half of the rope? Since it's less force or less work to pull it up?
Actually, it should be more work
Right.
because
So wouldn't it be 25 to 50 would be the first half?
I'm setting the origin at the top. So I'm assuming I'm at the top of the building and yanking the rope up. So
Okay.
if I put the origin where I'm at the top, I should be setting it up so that the top, literally the very top rope gets pulled up 0 feet. And then at the top, I should say the top bound, at this point I've pulled up half the rope. I've pulled up between 0 and 25 feet. So it has to do with where I mentally placed my origin at the top of the building. If you place it at the bottom, that gets a little tricky because we can actually ignore the 120. I think it just makes sense to place the origin at the top because it makes for a cleaner integrand. And by the way, on this one here, I was playing with this one earlier. It works out no matter what, as long as the bounds add up to 25, because I actually did it with 0 to 25 here. My thinking was I've already pulled up the top half. The bottom half should just be 0 to 25 as well, treating it as like 2 separate questions. And it worked out actually, because you would still get 25 as a difference. All right.
Okay.
All right. You should expect some more questions like the inverted cones, like the one we just did, a rope question, probably get at least you're probably gonna have about you should expect at least one quick question on sequences. And then definitely you should be expecting some questions on solids, rotating and slicing. And we kind of concentrated on that last week. Are there any questions you want to look at from that part of the stuff?
I have a quick general question.
Uh-huh.
So when it comes to volumes, how do you know specifically to use washer, cylindrical, disc? And subsequently, how do you know when to do dy/dx for each of those?
Well, in a lot of cases, it doesn't matter. I guess it's just a matter of what's easiest. And in fact, I'll give you an example. I'll give you kind of an easy shape here. Suppose I take a region here, it's y equals x squared between 0 and 2. So this is the region. Call it R. If I rotate R around the x-axis, the shape would kind of look something like that, right? And to me, just slicing it through the traditional way, it seems like discs would work the best. It would be pi from 0 to 2. So pi on the outside, integral from 0 to 2. It would be the radius. So each of these guys would have a radius of whatever this distance is. So it'd be x squared dx. Okay. Now, if let's say I take that same region, but this time I go around the y-axis. So the same region, this time around the y-axis. Well, the question is that I could slice it this way, or I could slice it this way. If I slice it horizontally, I would get washers. And that would work. If I slice it this way, I would get shells. Okay. And both work. So it's really just a sense of which one looks easier to work out, I suppose. If I set it up as washers, so I'm going around the y-axis, this y equals x squared. This would have to be a dy integral because I'm setting up in the y form. So x would be square root y. And washers requires it's 2 pi and then integral and then the distance. No, I'm sorry, I'm thinking shells. Let's just do washers. It's still going to be pi. It'd be a dy integral. Bounds would be 0 to 4 because I'm on the y-axis. It would be the outer shell, the outer surface, which would be just be the 2, so 2 squared, minus the inner surface, which would be the radical y quantity squared. And that would be my integral for using washers. Washers are just discs with a hole in the middle. For shells, I'm slicing it this way, so I'd use a dx. The bounds would be 0 to 2. I have to come up with a radius figure from the axis of rotation out to this shape, so that would just be an x. And then I just go with the height, which is x squared. And that should work just fine too. In fact, so these should give you the same answer. And really, it's just a question of which one looks. But actually, they both look kind of easy to me. But so to answer your question, sometimes you just have to draw it out and just kind of decide which one just looks like less work.
Or
Go ahead.
sometimes the choice can be made for you if you then can't easily rewrite the function as then a function of the opposite variable.
Right. That's true. Sometimes you get a function where solving for the other variable is impossible. And so you're kind of stuck with one particular direction.
That makes sense.
Okay. And also on these, just remember you have to take into account, like if it's being rotated like off one of the main axes, you have to account for that in the radius part. So the radius parts have to be accounted for. That you just have to be careful with that. All right. Okay. Any last questions? We've got about 10 minutes.
In 7-6. I would also like that, but someone said you might have already done a spring one. Did I miss that?
Professor did number
Oh,
3.
7-6 number
Professor
3.
Smith.
Is that from Infinity? Let's take a look at that one. Yeah, let's do a spring one. Because I did the number 3 from the Canvas review questions. So 7-6 number 3. Ah, yes. That's a good one. Thanks for asking. So I'm going to share the screen. I always confuse myself. There we go. 7.6 number 3. Yeah, there we go. Suppose that 2 joules of work are needed to stretch a spring for its natural length of 30 centimeters to 42 centimeters. So the 30 is the natural length. So I'm going to make a note of that. That's its rest length. How much work in joules is needed to stretch it from 35 centimeters to 40 centimeters? Okay. So it's this one right here. Let's do that one. So we have Hooke's law. It's actually just I think it's F equals KX. It's a real basic proportion. And so we need to figure out, we do know that it takes 2 joules to stretch the spring from its natural length. So what we have to do here is actually convert everything to, we're going to assume 0 is the natural length. So that would be 42, well, that'd be 12 centimeters. And we have to do this because this is joules, which is Newton meters. We have to convert it to meters. So what's that, 0.12? Everybody catch that? So what I'm doing here is I'm figuring out what K is. I need to figure out the K constant for Hooke's law. So I just work it out. So it's going to be K times x squared over 2 from 0.12 down to 0 equals 2. Just work it out. It's 0.12 squared over 2. 0 just drops out. Get my calculator out in a second. So 0.12 squared divided by 2, and then multiply that over the times 2. So back to point K is 0.0144. I think it's a unitless number. All right. Then I go back to my integral. Now we want to do it from 35 centimeters to, I wrote that down wrong. Sorry, give me a second. 40 centimeters. Okay. So I need to, now I've got my K, it's 0.0144 x dx. I'm going from 35, so relative to the rest state, that would be an extra 5 centimeters or 0.05 of a meter. And then this would be 10 centimeters off of rest, so 0.1 of a meter. Right, let me pause there. Does that make sense how the setup went about?
Okay, so do you not have to, I was thinking about going from like at rest to 35 and then at rest to 40 and like subtracting them.
That should work because, well, first of all, you have to get this figure. So I'm assuming you've gotten this figure already.
Yes.
Okay, then if you were to do it as 2 separate little integrals, like from 0 to 0.05, and then 0 to 0.1, and then subtract, that would work because that's actually what that is.
Okay, it just makes it easier to do it in one.
Yeah.
Sorry, Shannon, I didn't mean to. May I ask why the K is not minus? Because it's a force of a spring, so the direction would be moving in towards back to its state of rest,
That's a
right?
good question. I think at this point we're not really worried about, I guess you could say we're not worried about a vector form. I don't have an easy answer to that one. I've always known it as just K being a positive constant value. A lot of it just depends on like in what application you would be using K. If you superimpose an XY axis system, for example, when you take differential equations, you do a module on springs, spring damping, and you actually do use Hooke's law. And what we do is we set it up in such a way that the spring hangs down. And then we actually define down to be positive direction. And that way K stays positive. And it's just really nothing more than a convenience. That's it. So a lot of times we can get away with kind of artificially saying like down is positive just to keep the arithmetic easy.
Thank you, Professor.
Yeah, I hope that makes sense. Let
And
me just finish
Professor, can you
this
just
off.
clarify? In the beginning, you mentioned we have 2 joules, and you said that it has to go to, or we have to convert it to newtons or something. Can you just clarify what part that is?
Oh, actually, yeah, let me finish this off real quick. I've almost got it. I just getting the number crunching going. All right, hold on. Okay, yeah, you know what? I'm trying to do things at once.
Yeah, no worries,
The
Professor.
joules by definition is Newton meters. So you don't have to actually do any conversion. In this case, joules is Newton meters. And the only reason I illustrated Newton meters here is because the original problem had it stated in centimeters. And that tells us that we have to convert centimeters to meters. So that's the only reason I emphasized the meters part of it, because that tells us that when we go about doing like our bounds on our integral, it's got to be in meters. And it's real easy. You might think just 0 to 12 right here, right? Well, unfortunately, that would get you in trouble because that would be 12 meters if you weren't careful. And this is only 12 centimeters.
And could you technically just keep that 0 to 12, and that would be, I guess, 5 to 10 in the second integral, and then we would just get the final answer and divide that by what, 100 or something for the centimeters? Would that work out?
I don't feel comfortable with that. I think when you start squaring stuff, you start introducing. No, I'm going to say no. No, it's probably easier just to go with the conversions up front, and then just let their natural arithmetic follow.
So in general, if we see anything other than meters, just multiply or divide to get it to meters.
Right. If it's in joules, if you get a problem that's stated as joules, you've got to be in meters. Okay. If you get a problem in millimeters, well, you got to convert that to meters using the 0.00, the 3 decimal places.
Thank you.
Yeah. So I'm going to finish this off. And actually, again, I'm kind of messing myself up. This is actually wrong. This is actually I should have divided and multiplied. So this actually just becomes 277.78. So I just wanted to finish this off. 75. Yep, that sounds about right. About 2.08 joules. All right, well. All right. Well, guys, it is 7 o'clock where I'm at. I appreciate you guys showing up for this. I am recording this, and it will be placed on I'll send out a link, and it'll probably be about an hour before it's ready to be reviewed. Otherwise, I wish you all the best on the exam. And, if you can always ask questions on ed discussions relating to any of the homework or reviews. So that's always legal. You just can't discuss the actual test. All righty. Anybody have any last questions? Sorry for my sloppiness. All righty, guys, I'm going to go ahead and end this. So 3, 2, 1.
Thank you.
Thank
Thank you. You all have a good night.